I don't know how about you, but whenever I start playing a new game, I know I'm in trouble because I usually get really excited playing all kinds of games because I like to win. And usually it ends with me getting hurt somehow. A couple days ago, I played a card game with some other guys, and it was a fast card game, and we were both, well, the guy next to me and I were aiming at the same pile of cards, and we hit each other's arms really hard. So I was still in pain the next day. It gets even worse when I play the pinball machine. I don't know if you know that feeling when you see those milliseconds when the ball gets closer and closer to the flippers, and you know it goes straight through the middle, and you actually have no chance of hitting the ball and keeping it in the game. But nevertheless, you keep trying, and you push those buttons really hard, trying to keep the ball in the game, and then you hurt your fingers and punch the machine. Anyone who knows that feeling? Okay, good. I'm glad I'm not the only one then. Well, how cool would it be to have your own custom pinball machine? I mean, one where you can pick out your favorite LEDs, or you can build your own design and everything. Lucky for you, we got someone here who's built his own pinball machine and who can tell you exactly what you can do. He's a computer scientist. He's actually right now doing his PhD in computer science. One of his favorite hobbies is pinball machines, and he uses this experience he gains from playing pinball machines to learn more about manufacturing hardware, game design, and real-time software. Well, I'm pretty sure if you're loud enough now, he'll show us some pictures of his own pinball machine and give you an expression or an impression of what your own machine could look like. So please welcome and give a warm round of applause to Jaap.
Thanks. Yeah, good afternoon, everybody. My name is Jan Kantot, and I actually started building my own pinball machine about 1.5 years ago, and I will tell you about that. This talk will be mostly pictures, a few bullet points, and this will be basically our outline today. So we start with game design. So how do you want your game to look? What kind of toys or mechanics do you want in there? And then we skip to what mechanics do we need? Then how to control those mechanics. So which electronics we need to control them. Then how to drive the electronics with software. And then now we theoretically know how this works, and then we actually do the hard stuff, building all the parts for it. And at the end, I got a small lessons learned. If we have time, I got a video of our machine actually running a game, and you may ask some questions if you like. But let's start with what is pinball. This is a pinball. It weighs 80 grams, and it's 27 millimeters diameter. So if you want, I will give some through the audience, just to give you a feeling how hard a pinball is, and just hand it around. Yeah. And this side. And not everybody had it yet, but you will notice that this is actually more heavier than you actually thought, probably. And yeah, pinball is about shooting this nice ball around in a machine. So it's actually a machine with all the consequences. So I'm a computer scientist, so I'm not used to mechanics and all this stuff. I know a little bit of electronics, but yeah, mechanics were new to me. But let's start at the beginning. Small warning. Inside a pinball machine, there are high voltages. Just turn them off before touching them, maybe. Then you get coils, and they can hurt you. And if you drive them incorrectly, they will also burn. And they can also burn down your house. This is an expensive hobby. And it takes a lot of time and effort. So maybe consult with your girlfriend or better half before. But if you're fine with this, then let's go. So I met with a friend, and we actually decided, well, we want to build a pinball machine. So actually, at first we were drunken, and but the next day we still remembered it, and then we said, well, how could it be? So I made this beautiful drawings here, and for God's sakes, they're no longer in the artwork. But we wanted to make a machine which is for 2 players, not 1 player, but 2 players. So a head-to-head pinball machine. 1 player fighting against the other player. And we wanted to be good versus evil. So this is obviously evil, and this is maybe good. Yeah, so we selected a theme. And yeah, then some artwork, okay. We come to better artwork later. Then we wanted some medieval theme for the music, and then we also picked the general color scheme because you have to have a lot of decisions for mechanics, for graphics, and you want to make sure that you don't have to redo everything at the end. So we also pick colors. In our case, it's more blue for the good side and black and red for the bad side or from the evil side. And the girlfriend of my friend with whom I'm doing this, she's a teacher. So we started with this. So it's full-size playfield here. That's a kitchen table. And we just started off moving around parts. So how should the layout look? You have to do one basic decision at the beginning. Do you want to have a standard body or a wide body machine? The standard body machine is 50 centimeters or 20 inches, and the wide body machine is about 25 inches, so 60 centimeters. That's a general decision, and if you closely look at different pinball machines, they play quite differently. Even if it's only 10 centimeters, it plays differently. So we decided to go with a standard size. And then we started with the standard lower third. The standard lower third is basically slingshots here, some flipper fingers here, trough in the bottom, and the ball is shot here. So that's very common on nearly every machine. Then we have some pop bumpers here and some colorful ramps here, and that's how we started off. And we started to imagine a layout and which toys we want. And basically which mechanics we need to achieve the effects we want to have. Then we designed a little bit more and came up with this. This is actually our first design for the lights. Where should the lights be? So we drew this on paper, and it's pretty similar to the machine at the end. Not quite, you will see later. But just plan ahead, because changing stuff later with real mechanics or hardware is generally expensive. That's even worse than in software. Late changes just are a lot of effort. So do them early if you can. And next, we did a whitewood. A whitewood is a name for basically a prototype playfield. Usually it's done of wood, but we decided to go a little bit lighter, and so we used foam core. It's basically a foam with 2 paper plates on top and on a bottom, and you can cut them with exciter knives. You can hot glue them. It's really cool, and you can use gaffer tape everywhere. So we built it up this, and just we were creative, and we tried a lot of stuff, ripped stuff off, and put it together differently, just to see how it feels good. And then we went sophisticated and designed it in a CAD program, and the playfield looks like this. So let me just walk you through this machine. The players are here, and on the other side, those playfields are identical besides the artwork. We got 2 flipper fingers here. We got slingshots here, which push the ball away. We got the shooter here, but the shooter doesn't go into the playfield like in most machines. Instead, the shooter goes over to the other side, so the ball comes back here and stops here. Here's a post which stops the ball. And then we release the ball from here into the playfield. And after we released one, we just shoot another one there. So that once you lose a ball, you instantly get a new one. So it's just a flow machine. There's no stop and flow. There's just flow. You always got a ball until you lost. Then we got some ramps, and two of them, this goes over to the other playfield, and a little bit hard to see here, but I got another one. The center ramp here, it also goes over to the other side. And it comes basically back here from the other side, and here's a lock. So this can keep 3 balls, and once you're under attack from the other side, there's a certain mode which you can achieve, and then it will release up to 3 balls from this lock, actually. Then you got this nice star here that will be some kind of bash toy, so a figure on one side, an angel, on the other side, some kind of demon. And you can shoot them. There's a drop target in front and a target to actually attack it. Then we got one loop ramp here, which comes from here. So you shoot it from the right flipper finger, and it goes back over this wire ramp to the left flipper finger. We got the same on the right side, a ramp here, which goes here and to the right. So you basically can shoot from here to this side. It comes back on the left side. You can shoot from the left side to the right, and it comes back to the right side. So you can switch the flipper fingers if you like. There's an orbit here, which goes into a kicker. This can hold the ball for a second and then release it into the pop bumpers here. And you can also shoot the orbit from the other side, and it goes around the orbit, comes back. And we got a scoop. Here, it shoots just to this ramp. That's the basic layout. We came up with this after playing with foam core and trying a few revisions. So now, imagine we got this in a CAD program. What do we need to actually build this? And it turns out we need mechanics, because the ball won't move on its own, at least not for very long. And the standard lower third is basically 4 parts. It's flipper fingers, because this is a CAD drawing here, but you will see a nicer picture in a minute. You got slingshots, you got a trough which keeps the balls and ejects balls, and you got a launcher which launches the ball into the playfield. So that was our first build, basically. This is foam core again. This is not real wood. This is foam core. Foam core is 10 millimeters thick, and a standard playfield in pinball machines is 13 millimeters thick. So it's an unusual size in Germany, basically, or in Europe in general, because it's inch. So for most mechanics, it works fine. In the lower third, it works. But for some mechanics, you just have to put another 3 millimeters below. Otherwise, they will just stick out too much from the playfield. This is a trough from below. It keeps the balls. This is a flipper finger. Those are slingshots from below. This is from above. There are 2 blade switches. And this is the actually kicker. It kicks the ball like here. And those are the flipper fingers, or the flipper beds on the upper side. The trough collects the ball here, or it drains there, and ejects here, and the launcher just ejects to the playfield. So that was our first build. Trough, in case you wondered how this works, it's pretty simple. Basically, the best flipper mechanics are always simple. They work better if they are simple. So it got multiple ball positions. They just rolled down in the trough. There are 2 rails on the bottom. And then for every ball, there's 1 switch to detect if there's a ball. So it basically counts the balls here. And when a new one drains, once it sits on the switch, we know that the ball drained. It has a coil here, which ejects the ball out to the shooter. And there's a special jam position. There's also usually an opto contact to detect this, because it's very usual that the ball just comes back, because it's mechanic. It's not 100% reliable. And you want to pulse this coil a little bit less, because otherwise both balls will go out. So that just the upper one kicks out. This is how it looks in our machine. This is the trough. From above with at least 2 balls, and this is the kicker. Usually there's a spring which you can pull and to manually launch the ball, but in this case we only got an auto launcher because now the machine will feed balls to the other side. So it would be bad if you can keep the balls away from the other player. So this is also a little bit more reliable. We switched those mechanics. We had another one before. Then we got some more mechanics we need that's very basic, and you can find those in nearly every pinball machine. This is a vertical up kicker or a scoop. This is a scoop, but it's also a vertical up kicker depending on the naming. It's a vertical up kicker if it kicks it up to a ramp. If it's a scoop if it kicks it back to the playfield, and it's a kicker if it doesn't fully go in. So basically those are all the same, but just with 3 different names. And they work by having a switch like this, and just to notice that there's a ball and the coil, you can see the shaft here, which just kicks the ball out. Here it actually falls in, there's also a switch, and it shoots the ball into the ramp. It can also just pulse the coil less, and it will go back to the playfield. Also works. Then we got pop bumpers, very, very common mechanics, and they make those nice noises of the machine. That's how they look from above, and this is how they look from below. Basically, this is a switch plastic, and this actually moves here, this shaft here, which triggers this switch. It's kind of complicated, but it works fairly well. And then you got this coil, which pulls down this metal ring here, which pushes the ball away. Very common mechanics, you can buy them, and usually they work pretty fine. And here you can see that we glued another 3 millimeters of foam here. Otherwise, the switches will just not fit at all. So, but this still works on foam core, so no need to make wood so far. For prototypes, it's really, really good. I would totally recommend it, but there are other opinions. So some people say, well, no, just do it on wood initially, but I would recommend foam core. Then you got some other mechanics. This is simple. This is just a blade switch with some green plastic on top. So those are targets, and you can see them everywhere in the machine. And you got drop targets. Drop target is a plastic shaft here, and once you hit it, it goes down with spring. And there's a switch to detect this, and a coil, this one, which just can pull it up again to reset it in software at the end. And those are very typical mechanics you can see in a lot of machines. We got one special mechanic, which is basically a diverter. I showed you this playfield before. And what happens if one player constantly drains balls? Then at some point, there will be no balls in the trough at the other side. So we need some mechanic to balance the troughs. And this is done by this nice mechanic here. This is basically a diverter. It's a flap, and we shoot the ball over, and we can just enable a coil, which is below here, which will push the flap up, and the ball will just jump over. And then it drains on the trough below, basically. In a normal case, it will just drop in here, and we will hold it with this post, which will go up. So this is basically a lock, which temporarily locks the ball, and once we need it, we will release it. This is the other lock, which is fed from the ramp in the middle, so it comes over from the other side. It comes from here. And then we got 3 positions with optos here, and again a post which can just go up and hold the balls, and we can release them even one by one. So we don't have to release all of them. So where do you get those mechanics? So obviously you could take a machine and just strip them out. Will work, and it's probably also the cheapest way to do it. But those will be old mechanics, and you have to clean them and so on, and not everything may be available. So it might be better to just buy them, and it turns out that's totally possible for most mechanics. Just check out the manuals of the machine where the mechanic you like is in, and their part numbers, and you can just order them. In general, it's good to order assemblies, which are just a collection of parts, because usually, for example, a flipper finger, that's 15 to 20 parts. And if you order them separately, that will be expensive very, very quickly. So order assemblies if possible, and there is one shop which actually sells those mechanics, and they build them on their own, also for very old mechanics. So look what they have. It's usually a good idea to just check what they have, and those are very well priced. Usually it's Pinball Live. And you can also write them an email, and if you're lucky, they will build the mechanic for you. Say, well, yeah, it takes half a year, and then we have it. Haven't. Then there's Marco's Specialties. They got everything, like really everything, but usually only one or two, and old stuff, but they got, I don't know, maybe 10,000 parts or so. They got really everything, and it's at a high price usually. Then you can go to your Stern distributor. If it's a recent Stern machine, that's the largest pinball manufacturer, and they sell replacement parts. It's usually not that expensive, but it takes a lot of time to get those, and sometimes some effort. But I guess they will even produce those parts if you're willing to buy them. So those are your options. You can also build mechanics like we did on the diverter, but I showed you the third revision. So that took some effort to make it reliable, because that's sometimes not easy, at least not for a computer scientist like me. So now we got mechanics, and we bought them, and well, they're in there, and yeah, now we need to control them. And I'm working on an open source project which is called the Mission Pinball Framework, and it's a framework which can control all those mechanics. So you can say, well, there's the flipper mechanic, this is a button, and this is a coil, enable it, and it will do all the magic in the background. So it contains a lot of building blocks. It works on Windows, Mac, Linux, and for example, Raspberry Pi, which is also Linux, but with some special limitations. Then you need a pinball control system, which usually interfaces with USB to your computer. And there are three major ones. It's Fast Pinball, Multimorphic, P-Rock, and the Open Pinball project, which is actually open hardware. And this is a little bit basic, but also works. It's also the cheapest option. I got them all here. So if you want to have a look later, just come by and you can show them. And then you need obviously a pinball machine. You can retrofit an old one. You can build your new one, whatever you like. Then you need driver boards. Those usually come with this control system. And they, even in traditional machines, they're typically separated from the CPU, because those are the boards where the power is actually, which even may burn in some machines or cause damage. Then you got it has those FETs which drive the coils, and those sometimes burn. For example, if you got a charge in your coil, then those might burn and you have to replace them. They also got input protection, so your CPU won't burn once you connect your input to coil power, for example. So you can buy those, or you can build the Open Pinball project hardware, which I can show it, which looks like this. So that's the cheapest option basically. This is basically $40. But you have to solder it on your own. Then obviously you have to wire it up. This is how this looked for our standard lower third. Those are the control boards here. And yeah, use thick enough wires, because coils carry a lot of current, at least initially. So don't take too thin wires, otherwise they will just burn away. Then I talked a lot about coils, so I figured I need one slide about coils. They're used basically everywhere because they're cheap, they're reliable, and they're fast. For example, you could use a servo, but it will go out and it takes a lot of time, and it's expensive compared to a coil. So usually they're driven this way, that they initially pulse for 5 to 20 milliseconds something, and then they hold with PWM. So they enable for 1 millisecond, disabled for 6 milliseconds, enable for 1, and so on. Because otherwise you won't have enough power. For example, if you want to kick a ball, you need a lot of acceleration in the beginning. So you need a lot of current there. So usually they got an impedance of 4 to 8 ohms, or a little bit less. So they carry a lot of current, or and they can burn, obviously. So if you just connect them to your PSU, they will burn usually. That's why it's important that you PWM them, and do not, unless you know what you're doing, do not just enable coils. They will burn. Try it once, but do not do it in your pinball machine, yeah? And they can hurt you. They actually have a lot of force. So you probably all tried the ball by now. It can shoot this ball pretty fast, and it can also shoot your fingers, for example. And that will hurt, I can tell you. Then you want to know where the ball is actually, and this is done by switches. So there are two traditional approaches here. One is those blade switches, the simplest and most reliable switch basically ever made. And this will basically always work. You can have a target here, you can have a button here. If it's possible, they usually go with those switches. And in newer machines, there are also those micro switches, usually from Cherry, like in your keyboard. And for example, with this custom blade here. So this goes through the play field, and this is basically a rollover switch. So if the ball rolls along there, it will notice it. And the control system will get this pulse and tell the software about it. Then we got optos. I showed you some before. So the most common ones are those. Those are the Williams or Stern optos. They're about 13 millimeters thick, so you need a lot of space here. And we forgot about that, or we didn't actually know in the beginning. And a lot of places we didn't have 13 millimeters. So we needed to come up with another solution. So we 3D printed this part, which is a side LED. This is 1.6 millimeters. And you see it connected here to a 1 millimeter steel ramp. This was the first design. So it worked pretty well in the beginning. But then it turned out vibrations are bad for this. And it clips through the hole here, but it's not enough. Sometimes they will just fly off. So we redesigned it like this, so that the LED goes in from here, and you can screw them into the ramp. So we cut threads there, and then you can screw them in. That was the final design, but it took some iterations. So now you know, and you can do better, hopefully. Next is we needed to connect those optos to the control board. This is the control board here for the inputs. And we designed those breakout boards here. One for power, for the current limiting resistor, because every opto is basically an LED and needs current limiting resistor. And you don't want to solder them into the line for every single opto. So we designed those breakout boards, and one for the receiver side. You could just crimp those receiver sides here, but then you could never disconnect it again, because there are 2 wires from the opto and they go down, and then you got 8 optos on this bank of this control board, and this is on the bottom and the optos on the top. You will never be able to disconnect it. So we went with little small connectors, and then you can pull them out. And then we need lights, and today everybody wants RGB, right? You know those blinking light people. It's boring if it's just one color. So you got 2 types of lights basically. This is insert lights, which are basically those things here, which are plastic and a light below. And you got general illumination, GIs, which are below the rails and everything on the side, just to light the playfield from the side. And we use those nice Christmas lights for the general illumination, and those WS2812 LEDs, which come in this nice package here, to screw them from below. We did another playfield, which is foam core again, just for the lights, just to test light shows, and we didn't build it in our actual prototype. So next you need a display. So there are different options. You can use an LCD display if you like, but then you need high definition graphics, and it gets a lot of it costs a lot of effort in game design and graphics rendering and video rendering, and those small displays, which are basically DMD dot matrix displays, they only have 128 x 32 pixels, so it's a lot easier to make graphics for them. So we went with those, and because we are head-to-head, we need two of them. So this is in software. You got the two DMDs, and one is on every side. And this is actually an LED matrix, which we bought, and this can then actually show the same thing, which is shown here in software. Then you use power, and usually in older machines you have 70 to 80 volts with those nice transformers here. But nowadays, I would recommend a switching power supply with 48 volts. They work fine, and you can buy those for 50, 60 bucks. We went with the old one because 3 years ago they weren't readily available when we bought those. Then you need 12 volts for switches for the switches on the playfield, and 5 volts for all your lights. So if you go with serial LEDs like we did, you need a lot of power on the 5 volts. So we went with an ATX power supply, but there are cheaper options for this. And we went with the transformer, but switching power supply would be better probably. Then, now you got all the basics. So now you know everything to do it on your own. Well, but we didn't actually build much. So let's get started with this. You need a playfield, which is, as I mentioned, 13 millimeters thick, and at the end it's Baltic birch, and it's sanded to 13 millimeters, because if you glue in those inserts, then you have to sand it down. You can decide between standard and wide body, and you can make it between 1.6 meters and 1.16 meters long, but it doesn't matter much. As I mentioned before, the width actually matters. It feels a lot slower if it's wider. I showed you the prototype in foam core, and another option would be to hand root it in wood. And the final version would be you would do it with a CNC machine. And just as a reminder, that was the first machine we built in foam core. Like even the RAMs, everything is foam core here. Works fine. Sometimes you just have to re-hot glue stuff because this ball is heavy. It will shoot off stuff. But yeah, that's foam core, and it can fix everything. And then we went more professional, and we used the CNC machine to build the playfield. This is actually where we cut our playfield. Took about 15 minutes roughly. But at a professional manufacturer, there's one in Germany actually, which does playfields, and he did this for us. Yeah. Then afterwards, you usually glue the inserts, and you sand it flat. Then you print it, and at the end there's coating. It's like car coating, but a lot more layers. And you probably do not want to do this on your own, unless you're a professional painter or something. Then maybe, but otherwise you do not want to do this. At least we decided not to. This is how the wood version looked. So we didn't do inserts at the beginning because it's expensive with all the coating. So we took the simple version and just built the same playfield again with wood. So it looks a lot cleaner now. So this is all the lower side with all the electronics. And this is the upper side with the RAMs. And next, so we're currently doing a next version, which we hope to have it finished for Congress here, but it's not finished yet. It will be finished in January. But but this is the CAD drawing basically with also insert where they should go. And this is actually how it's done. There's a nice robot which can glue the insert for you. At least if you do more than maybe 10 playfields. So for professional machines, it's done with a robot. It just sucks the insert here and just puts it down, and then it's glued. We did some artwork with Photoshop. My colleague is actually called Philip, so Photoshop Philip. It's probably a German joke, but it still works. Yeah, this is what you came up with. It's not a final version, but I think you get the idea. This is probably too light. This may be too dark at some point. It's too much contrast between the two. But you get the idea. This is obviously the evil side. This is the good side. But the inserts are the same, and obviously the holes for the mechanics are the same. Just different print, and the software will just drive it differently. So now you know we need all the hard stuff, so like metal. So let's build some rails. So at the edge of the playfield there are those rails, because if you shoot the orbit, the ball should slide around and not just go to the top and fall down. So those are typically made of steel, and we initially just got 2mm steel band from Amazon. It was pretty cheap, and then we braced screws to it. That's what you can see here. You just brace screws to it. Doesn't look pretty, but it worked for a long time. And later we lasered them. We'll show you in a minute. This is when we mounted this handmade prototype rails, and we had them for quite some time. They worked pretty well. Afterwards, I designed them in CAD again with a sheet metal tool with all those nice latches here. And then we basically unrolled them for this, and this is what our manufacturer sent us five weeks later. And then we bend them by hand. It's 1mm steel, stainless steel, and this is how one rail looked like. Unfortunately, I don't have a nice picture without the ramps on top, but I think you get the idea. This is just the rail around the orbit here, and it has some nice latches where you can screw it to the playfield. Yeah, so next we need some ramps. So you get different options for ramps. One is plastic. You can just 3D print them, but they're large, and it takes a lot of time and probably filament, but it works. If you want, you can do this. Later you would typically deep draw them. That's also doable at home. And a lot of people do it. We didn't. We went with metal. This should be solid. And so first we actually cut them by hand, and at the end we lasered them again. And you got wire ramps, which you usually use where a metal ramp would just hide too much stuff of your playfield. So those coming down from the top, those are wire ramps. And you can weld them again, or you can weld or brass them. So this is again the ramp setup. So those will be wire ramps because this will hide too much of the playfield. You just want to see the inserts and the nice artwork below. And this will be steel ramps basically. So first we went again with a CAD program, and then we did this nice prototype out of cardboard. And you may laugh, but this works. For some time until this flies away here because the ball hits it. Until that point, it will work. But for prototyping, it's fine. It just put them in there, hot glue them, and it will work. It will work. Then we cut them by hand. Doesn't look pretty, but it worked even better. Especially it was faster there. And then we went more professional. So the bottom one was the handmade one, and the top one was the professionally made one, which we didn't bend by hand because we missed to cut them here. Then we did it again, and like a lot of things, we did a lot of iterations. So we currently do the 4th iteration of our ramps, the 3rd iteration of the playfield, and the 4th iteration of the rails also. So this is what we did next. This again what we got from our manufacturer. We just lasered out the bending slots, so you can bend them at home with a small bench. And that's what we did. And then it looked like this. We got everything twice, because 2 sides, and then you have to build everything twice. Should have thought about that earlier, but well, you learn from your mistakes. And then that were our ramps, basically. And there will be a new revision next year. So yeah. Then we did wire ramps, and we decided to go with brassing, with silver hard load. It's in German, silver brass alloy, I think it's in English. And you just use a torch and put the silver to the metal, and then it connects. It's pretty stable. So we didn't manage to break it until now. So it's easier to break it here than break this. So that's pretty okay. This works. I mean, it doesn't look perfect, but it works for quite some time, and we still have them. And this is actually before with all those foam core ramps, and afterwards with wood and all the real ramps and the wire ramps here. So you see that we still had a lot of foam core here and hot glue and gaffer tape for just connecting stuff, because you need latches everywhere, and you need holes to screw stuff, and you tend to forget this. And we didn't notice until we got this that steel, the V4A steel, is actually really hard, and you cannot easily just drill a hole. It will just go, and then it won't look pretty anymore. So we just went, well, let's do it again, put in all the holes and do a new revision with all the mistakes you made and fix them in the next revision. So now you notice that there's a lot of open space like here. And what the ball will do, it will just fall in and then stay there. And since there's no mechanic to push it out, well, it will stay there forever. And that's a problem, at least if you put the glass on top. But it's not good. So usually you got plastics. And in the beginning, yeah, just cut them out of foam core, like everything, and hot glue them. And then we went to 3D printing. That's what you can see here. And then, as usual, let's face reality. And there's always something missing. So there's some manufacturing tolerances at the rams, some tolerances when you bend the rams. And yeah, even if you just screw stuff, everything has tolerances. So make sure just to cut a little bit off here, and leave the ledge here. And yeah, and then we did it again. So like everything, you learn from doing it. So prototype everything. If you can laser it out from cardboard, we didn't have a laser, so a laser would be handy. So just laser it out from cardboard and try it out. It will save you a lot of time. Then you need software. I talked about the Mission Pinball framework. And basically, it's a framework. It's written in Python. It's Python 3. You can install it via pip. Just pip install npf, the Mission Pinball framework, and then it's basically installed. You need working OpenGL and SDL too. So that's why we listed the Raspberry Pi before, because the Raspberry Pi only has this EGL, this limited mobile OpenGL implementation. So we support Windows, Linux, macOS, and the Raspberry Pi. And this framework has 2 processes. One game process, which actually runs also logic, and a media controller process, which renders all the graphics, plays the videos, because your game should be pretty real time. I mean, it's not important that everything reacts inside 1 millisecond in the game framework, because what it actually does is it pushes the rules into this hardware controller. So it says, well, if this flipper button is hit here, pulls this coil for 15 milliseconds. So the hardware will take care of that. But still, if I hit the target, the game needs to say, well, now light this light, and this shouldn't be, I don't know, 2 seconds. The player will notice everything over, I don't know, 50 to 100 milliseconds. So this should be pretty real time. And the media controller stuff usually is not very real time. So loading a video may block. Everything involving I/O on the disk may block. And this also renders the DMD, which is connected to the game process again. So we send events to the media controller, it renders the DMD, we get that out of OpenGL, and then we send it back, and then we send it to the hardware. Because if you do not want to do everything pixel-wise, so we actually render an MPEG video on an OpenGL viewport and then just get the right pixels for the DMD back, just to make it easier for a developer. This is a general sequence how the software works. It launches, initial startup, initialize everything. Then you got an attract mode where you flash all the lights and tell the player, well, give me a coin, play me. And when the player does, there's a game start sequence where usually some sounds play. Then the ball starts, the player does something, the ball ends, and this repeats until the player has no more balls. Then the game ends. In our case, we got 30 lives, so you can lose 30 balls on every side, and whoever loses 30 balls first will lose. A little bit different, but we just overloaded some classes here, and then this mechanics work. This is how the software side works. You got the virtual DMD here, you got the state of all your devices in your software here, and you got the rectangle ones are switches, you can click them and they activate virtually. And the round ones are lights, actually. So you can see your light shows, and you can play with all the switches. You can say, oh, ball went here, and then the software knows that it's here, and it will carry on with this. It has some limited simulation, like if the ball goes here and this coil fires, it knows that it goes to the playfield, for example. So that's what it does. And those are our 2 playfields. We layouted them not head by head, but next to each other, just because it better fits the screen. So this is how this actually works from a hardware perspective. You got the computer, which connects via USB to the LED controller, which connects via serial to the LEDs. The DMDs are via USB. The controller board are via USB. Then we got a lot of node boards, which are basically just breakout boards for the coils and switches, which you mount below the playfield in modern machines. And then you connect the switches and optos and coils to those node boards. This is a general hardware architecture there. This is how it looks in reality. Our game runs here, transformer, there's the control system and some mechanics, and the LEDs connect to this nice fate candy board from Adafruit. We need a cabinet, and we do everything in foam core, so we did this in foam core too. This is a CAD model, actually, how it's supposed to look. This is how it actually looked. And yeah, there's some foil on the glass, but it's actually, believe me, it's glass. This is our back box, which is different from normal machines. It's just up on top, so you can see your opponent. And mostly this DMD is more for the observers. Most players do not look at the DMD during the game, because especially in our game where you always have a ball, you don't have time to look up. Otherwise, we fucked up. We did sound. I did this, so it's music. But if you seriously listen to most machines, the background sound is so simple. It's just, I don't know, it repeats after 20 seconds, and it's simple. So it works. It may improve in the future. That's why I won't play it now. But you can play it at home if you like. Then you need to play sound. So we built our professional sound system with a $60 China amp and a large subwoofer, like every car has. So it's actually car audio stuff because it's cheap. This is about $90. And yeah, we got basically one speaker on every side, and the DMD will go here. Basically, it's not in here yet. It's from the bottom, the back box from the bottom, and this is the cabinet from top. Yeah, that plays pretty fine. It's loud enough. It's nice. So what does this all cost? So and it turns out this is pretty expensive. So for our machine, just takes this by 2 because we got everything twice. Somebody should have told us. And this is basically just for the final version. So a playfield including print and everything is between 800 and 1,000 euros. If you go to some manufacturer and let them produce it for you. The cabinet including prints is about 500 to 1,000. For a normal cabinet, you can just buy one and then print it. For our cabinet, as I showed you, that won't work because of head-to-head. But usually I would buy it. Then the control system, depending on which one you choose, a commercial one or this homemade one, it's between 200 and 800 euros, including the PC. You got some electronics, depending on if you got silver or golden wires, and what strengths and what PSU, 100 to 500 euro. And then you got the mechanics, and it really depends on which mechanics you buy. If you got more mechanics, it will be obviously more expensive, but between 1,000 and 2,000 euros for just the mechanics. This is the part which would really be a lot cheaper if you produce maybe 1,000 machines. This would be maybe a tenth. But we cannot do it. We have to buy basically replacement parts, and that's why it's expensive. Then metal and plastic parts, depending on how many you do and how many you buy, 200 to 800. And the typical retail price of a normal machine is 8,000 to 10,000 euros. Recently, a little bit more even. And then you can see that this quickly adds up, and building a machine is not actually very cost efficient. If you factor in your time, then not at all. Never. So we got some lessons learned before I show you a last video of our machine at the end. General manufacturing is hard and expensive, and it takes a lot of time, actually. You go to a manufacturer and say, well, I want to build this, and they say, well, yeah, we can do it. In 8 weeks, you get it. And yeah, I mean, as an hobbyist, it's fine probably because I do not have unlimited time to build my machine. But still, I have to wait a lot of time then. Have everything in cut if possible. And it's nice to notice that parts hit each other before building them, because then, okay, which one do we throw away? Happens. I mean, most of the times it's hard to fix them. Then what we learned is the shot width. So if you do a ramp, it should be between 5 and 10 centimeters. The ball is 27 millimeters in diameter, so theoretically that will work already, but practically you will never hit it. So 5 to 10 is your range. Above 10, it's far too easy, and you always make the shot, and below 5, it's really, really hard. Then prevent jumps. Prevent jumps, because if the ball jumps, it will go somewhere, and then it gets stuck. I mean, it will get stuck anyway, everywhere. If it can, it will, at some time. So do not make ramps like this. Yeah, the ball will just go on and just fly over the ramp. Yeah, you learn that by prototyping. And finally, for me as a computer scientist, you cannot fix physics and software. So. So yeah, that's basically it. So our current playfield, so one of them looks this from below. So this is all the electronics. Now add all the lights, and then it's full. So there's not a lot of space left. This is how it looks from top. So one player here, one player there. Here with foam core decals. And yeah, now we'll show a video and at the same time take some Q&A. So thanks for listening. Yeah. So you saw here, one was released. and the next new one came.
Any questions? Now is your chance. Yes? Okay, give me the mic.
You said you had two computers, basically. One doing all the mechanical stuff and one controlling the whole playfield and the displays and stuff. But in your price calculation, you also had a third system, like a control system for 200 to 800 euros. What's that playing a part?
The 200 to 800 are your PC, like a Raspberry Pi, and your control system. This is basically just the node boards and the controller board. It will cost this amount. Then you have the electronics, which are the cables and the power supply. Yeah. And yeah, maybe the lights also. Yeah, if you add too much hot glue. That's
I think we have a question from our online viewers.
Yes, we do. The internet wants to know, or states that pinball machines have been around for a long time, and aside from modern manufacturing technologies, for planning and building with CAD and CAM, making things easier, have gameplay mechanics been modernized over the years?
That's right. I mean, the difference between old machines and current machines is that the rules are much deeper. So before it was just shoot this target 20 times and every time you get score. And the main objective was just to get an extra ball or extra credit sometimes. And in modern machines, it's like shoot this one 5 times, then we flash this insert there, then shoot this one, and then the other player gets the ball, and you get a nice animation. An insert here lights up, and you can start another mode. Basically, a mission is a mode in a pinball machine. So the rules are a lot deeper in modern machines, and that's basically because we have better CPUs in our machines.
A question over there?
Okay, well, first of all, thank you very much. This is totally awesome.
Thanks.
So obviously the physicalness of the machine, that's great. But did you ever consider simulating, not on a piece, to build a real scale model and project, CG render and project the entire game instead of building the mechanics?
There's virtual pinball, and you can play all the old games. You just take a 42-inch TV and put it into a cabinet. It actually fits, and add some buttons. You can buy this for, I don't know, about $1,000, and then you can do this. And there's actually one machine which is somewhere in between. It's called the Pre-3, and it actually has a TV in the playfield, but it has real flipper fingers on top, and you play the flipper fingers on top of the TV, and then there's the upper third, like this part, and you can swap those. So you can swap your games. It's still under development, but I think you can pre-order it, like you can pre-order everything 5 years in advance in pinball. But eventually it will be made, and I actually played it. It's pretty fun, but it's different a little bit because the contrast is different. Here you got a light which actually emits light, and there you got the whole playfield is light up because of the background light, and the ball is looking somehow black if it goes on top of the TV. But still, it's a nice machine.
Thanks.
A question over there? Okay. Any more questions? Now it's your chance. Could you go up to the microphone, please? Okay, we start on the left side. Go ahead.
I think this is the first two-player pinball machine I've heard of. Do you think this could become a trend if your machine is fun to play?
Well, there are actually 2 or maybe 3 machines. So they're a lot smaller, but they're from 1990 roundabout. So they're no longer produced for 25 years, but they still exist, and they do not have deep roots. The problem with our machine is actually that it's really, really large, basically long. It's 2 meters long, and you need basically 3 or 4 meters room for this. So you need a long wall in your living room or somewhere where you can put it. So this would be a problem in the market probably. So maybe we could make 100 machines and sell them, I don't know. But probably not 1,000. So I don't think it will be totally mainstream.
Okay, we got time for 2 short questions. Yes.
How are you handling the tilting of a machine? Because I imagine it's quite difficult for a 2-player machine.
Yeah, we got two accelerometers on every side. So actually, because you tilt them on your side, and then you can measure the acceleration there, and then you can see the direction actually. That if it goes this way, then you can see that the player on this side tilted it actually. And we just remove lives. That's easy, and if you tilt too much, then you will have no more lives.
Okay, last question.
Could you give us a time frame from first idea to the first game you actually were able to play?
We started last year in April, so it's 1.5 years roughly, and we were able to play before Congress, so I think in August, September somewhere, after camp definitely. But mostly because all this ordering stuff took about 3 months. And my colleague, Philip, he did all this sourcing and stuff and getting stuff from Canada and the US and getting it through customs. And it took a lot of time. So when we actually got the stuff and we had everything, the first build on foam core, I did the software before, and then we connected it and it just worked after 2 or 3 days. So that was pretty fast. But you could just shoot the ball up and it comes down and shoot it up again. It's not that much fun.
Sorry, we cannot hear you without a microphone.
So
Okay.
you talk about the dimension.
Only if it's a short question.
Just the shortest ever
Okay.
question. You talk about the dimension, but what about the inclination of the field itself?
It's typically 6.5 degrees. So, but you can go between 6 and 7. So, but standard is 6.5, and yeah, it just worked best.
Okay. Thank you very much. Thanks a lot, Jan.